Thank you for kind introduction. I'm Kanya Sui from Minebea Power Semiconductor Devices. It's due to by the stock transfer. We are from Hitachi, the ex-Hitachi Power Semiconductor Devices, and last year we have changed our name to Minebea. Maybe it's not used to you in semiconductor industry. Minebea. Please remember company Minebea Power Semiconductor Devices. So today, okay, can you see?
Should we explain how this name Minebea was chosen?
Yes. We have a subsidiary of Minebea Mitsumi. Minebea is coming from miniature bearing. So the company, come from Minebea. And today, I'd like to talk about the high current capacity power modules with sintered copper dioxide technology, and which is applied to silicon IGBT and silicon carbide MOSFET both. So I'd like to start with a brief introduction of the overview of presentation. After a brief introduction, I'm going to present the overview, show the overview of our developed modules. Then comparison of some impedance and other lifetime power cycle lifetime and current capacity will be exhibited. Okay. So, first, I'd like to give you some background information about the power module technology trend regarding the maximum junction temperature. It's our conductor power module. In the maximum junction temperature is the vertical axis, and the developed year is in x-axis. These are all Minebea ex-Hitachi 3.3 kV power modules, mainly for railway traction power module. So 3.3 kV power module is here. And for silicon carbide modules, we use small package in the right. These 2-in-1 standard package recently widely used in railway traction applications. And along with the transition from silicon to silicon carbide, the maximum junction temperature is raised from 125 degrees to recently 175 degrees. So next, I will explain regarding this why sintered copper is necessary. Here, power cycle next. Okay. Power cycle comparison was conducted for both silicon and silicon carbide devices. These are simple experiments for single die substrate using the conventional lead-rich solder. And the horizontal axis shows the cycles, and the vertical axis shows the temperature swing delta Tj, and the lifetime of the silicon carbide plotted in this triangle was approximately half or 1/3 of that of the silicon devices. Therefore, the silicon carbide devices requires more robust die attach technology, such as sintered die attach.
Slide.
Okay. Sorry. Then I'd like to move on to the brief overview of the developed modules. We have developed the 3.3 kV power module like this, and for both silicon IGBT and silicon carbide modules. It have common form factor with the footprint of 100 mm by 140 mm 2-in-1 package, which is named NHPD2. In recent years, in railway traction application, the new project is this package is adapted in the railway traction application instead of the larger package. And one of the reasons is this has a smaller inductance, so it fits to silicon carbide. And in right-hand side, the schematic cross-section of this module is exhibited. So the key technologies inside is the interconnection near the die. First, the silicon die attach of the sintered copper, and also the high-strength aluminum wire, and the hard film on top of the electrode. Here, you see a cross-sectional image of these modules, especially for the interconnection. It's a key technology of silicon IGBT power module. In the left, bond wire and the die-top electrode is shown here, exhibited. It has a high-strength aluminum wire and hard nickel-plated electrode film on the die-top electrode. And in the right, the scanning electron microscope and images of our in-house sintered copper layer die attach is shown. And this feature, this copper can be bonded directly to the copper substrate, and also the nickel backside electrode of the die. So this feature simplifies the assembly process. And also, the bond line thickness is 15 micrometer to 30 micrometer, which is approximately the 1/6 to 1/3 of the die conventional solder. So it contributes to reduce the thermal resistance. Then I'm going to look at the comparison of thermal impedance in the next section. These figures represent the cumulative structure function of thermal capacitance versus thermal resistance for the silicon carbide and both silicon IGBT power modules, respectively. Each figure compares the solder die attached module in black dashed line and sintered copper module in red solid line. The thermal impedance component to the die attach is indicated by arrows. So these components of the sintered copper were reduced approximately half for both silicon and silicon carbide power modules. This reduction was primarily achieved by the high thermal conductivity and the reduction of the thickness of the layer. Okay. And this in this table, thermal resistances and relative die area of each module are summarized. Yet, in both modules, compared with solder die attach, the sintered copper die attach provides an approximately 5% reduction in the total thermal resistance from junction to base. I'd like to point out here that the thermal resistance of the silicon carbide MOSFET module was reduced by 14% compared to the silicon IGBT, but the area of the die, total area, is reduced, differs by only 10%. So there is a mismatch. So the reason of this match is due to the smaller die and wider die spacing between the die, because the die size of the SiC MOSFET are approximately the 1/4 of that of the silicon IGBT. So the dies can be placed more separately. That reduces the thermal resistance. So I'd like to move on to the enhanced power cycling lifetime and the current capacity. Okay. Sintered copper die attach significantly enhance the power cycling lifetime. These figures compare the silicon carbide MOSFET module thermal impedance as a cumulative structure function measured during the power cycle at different cycles. So in the left, here, it is both silicon carbide MOSFET. The degradation of the solder die attach is observed in here. However, in the right, it's a silicon and sintered copper. Virtually no degradation was observed. So, and in the previous report, the lifetime of the silicon carbide MOSFET module with sintered copper was approximately 6 times longer than that of the solder modules. It was a previous report. And then, first, I'd like to exhibit power cycling test result for silicon IGBT. This temperature swing is plotted in the vertical axis, and x-axis is the cycle count. During the test, delta TJ, during the test, delta TJ and the TJ minimum increased because the thermal grease between the module and the heat sink was pumped out. So to continue the test, the grease was reapplied at 0.5 million cycles to very initial stage. After 1 million cycles, one sample was extracted for analysis, and remaining sample continued the power cycling test at 3.5 million cycles without failure. And the developed module showed more than 15 to 50 times longer lifetime than that of the conventional solder. Conventional one has 40 to 70,000 cycles lifetime. So to take full advantage of the extended lifetime of these sintered modules, it became clear that careful handling of the thermal grease between the module and the heat sink is necessary. So the cross-section images of the extracted sample were shown here after 1.5 million cycles for sample 1. So there's a crack in the army wire, bottom of the army area near the diode was observed. However, electrical characteristics of VC-SAT was stable even after 3.5 million cycles. So therefore, I think most of the electrical connections were presumed to have remain functional. Regarding the die attach, the sintered copper layer was analyzed. There's a cross section of the sintered copper layer, and in the center of the die, the vertical crack was observed a little bit. But these vertical cracks are known to be less significant on the thermal impedance, and also at the edge of the die in the right hand side, the sintered copper seemed to be intact. So these observations indicated that the sintered copper was robust enough to endure to over millions of power cycles. But once the power cycle count exceeded a million, then even the solder layer beneath under the ceramic substrate was impacted. This one, again, this vertical crack was observed in the solder layer below the die. But this impact of the thermal impedance is known to be smaller. Next one is silicon carbide. Then this one, right before, the temperature swing is plotted on vertical axis, again against x-axis of the cycle count. In contrast to the silicon devices, the delta TJ temperature swing and other parameters are continuously increased for the silicon carbide MOSFET module. The reason of this was the mixed effect of the thermal grease pump out and also the strong positive temperature dependence of the SiC-MOSFET, SiC-MOSFET conduction loss. The conduction loss are known to be that the SiC-MOSFET has a strong positive temperature dependence. So if the thermal resistance of the heat sink and the module increase a little bit, in such a case, the temperature is raised, and that temperature makes much more higher temperature. So this creates a positive feedback loop. So in the case of silicon carbide, at 200,000 cycles, the thermal grease was removed and reapplied. And after that, the delta TJ returned to its initial state, or almost same heating current. And the test actually continued 400,000 cycles without failure. So analysis by cumulative structure function also verifies that the degradation is due to the thermal grease pump out. These figures clarify the thermal resistance change during the power cycle test. The structure functions are overlaying around here, and this one, the diverging point of here is the border of the module and the thermal grease. So it's evident that the degradation occurred outside of the power module, and this one. So we need to improve that layer. And also, one sample was extracted midway through the test for 200,000 cycles. This figure presents the SEM cross-sectional images. In the magnified image, sorry, okay, this is still limited to no. In the magnified image, there's a crack observed in the center figure, but the length of these cracks are limited within a few hundred micrometers. And so the sintered copper die-attach layer shown on the bottom, these layers have almost, in fact, no significant current degradation was observed. So to summarize, this suggests that there is still considerable margin of lifetime remaining here. And also, the current capacity enhancement was estimated using steady state inverter simulations. These figures show the calculated maximum peak current versus carrier frequency for both silicon carbide modules. The output current capacity was increased by 20% for the left-hand side silicon IGBT, and also the 25% for at 4 kHz in silicon carbide MOSFET. And in the low frequency range, I mean the left side, the benefit of the maximum temperature increase was mitigated because of the steep and positive temperature dependence of the conduction loss of the SiC MOSFET. But in contrast, the switching loss is so low in case of silicon carbide FFET, so the frequency range is widened. The x-axis is different for both left-hand and right-hand side graph. So the silicon carbide MOSFET can be used for much higher carrier frequency. So in summary, the elevated maximum junction temperature and lower thermal resistance allows the nominal rated current to increase from the 600 to 800 in silicon IGBT and 800 amps to 1000 amps in sintered SiC MOSFET. So progress of power density improvement including this work was summarized in this figure. Here, rated power density versus developed this one. Rated power density is in the vertical axis, and developed year or reported year are plotted in the x-axis. So these are all 3.3 kV high voltage power modules. Blue square marks are silicon IGBT of the Minebea power devices, and red circles are silicon carbide of Minebea devices, and green one are silicon carbide or other manufacturers. So in this work, the shown right here, the rated power density of our module reached 38 kilovolt kV per square kVA per square centimeter for silicon IGBT and 47 kVA in silicon carbide MOSFET. So to the extent of my knowledge, it's a best in class, one of the best against 3.3 kV high voltage power modules. So let's go to the conclusion. This is the summary of our result. First, we have developed 3.3 kV 2-in-1 module with sintered copper, and also sintered copper, also with the hard nickel film and high strength aluminum wire. And the power cycle lifetime showed more than 15 to 50 times longer lifetime in silicon, and more than 10 times silicon carbide. And also the thermal impedance is reduced for both cases. then we have achieved the current ratings for 800 amps and 1000 amps for respectively. After this improvement, external thermal grease interfaces now a next bottleneck to limit the lifetime. So it will be one of the future work to improve his layer for more reliable power unit. So that concludes my presentation. Thank you for your attention.